Good morning, ladies and gentlemen. We are starting with our new STARS tutorial on technological innovation analysis. It's part 3, and the topic is assets for automated, autonomous, or remotely piloted operations and network management, planning, and control. This tutorial is one of 4 tutorials performed by RAILENIUM, and RAILENIUM performed a huge technological innovation analysis within the STARS project. I come later on to this topic. This tutorial is part of the European Week of Advanced Technologies for Railway Applications, and this week ends by today and included several tutorials. The STARS Hack and Match event we performed last week, and the still ongoing opportunity for virtual business meetings via the STARS Hack and Match events meeting platform. That is a B2B matchmaking platform normally used by the Enterprise Europe network in order to build up new business contacts, and the use is fully free of charge. And if you have a short profile on this platform, it would be easy to meet other participants, to ask them for about 30 minutes meeting, and then you could exchange whether a collaboration is fruitful or not so fruitful. The platform will be available for the moment until the end of the project. It is the 30th of September. We are in a discussion to keep this platform sometime after the project, but the decision has not finally made by the European Commission. Yeah, the cluster collaboration, the STARS project, Strategic Alliances Boosting Railway SMEs, is to support European small, medium-sized enterprises of the rail supply industry in successfully adopting advanced technologies to boost products, services, manufacturing processes in organization. It contains of 10 cluster organizations, 5 technology centers, amongst them RAILENIUM, 1 digital innovation hub, 1 blockchain provider, and 30 supporting organizations from 14 countries. Yeah, I'm a member of one of these 10 cluster organizations. My name is Lutz Hübner from Berlin Partner for Business and Technology. Yeah, the innovation trends which drive the development of products and services in the rail sector until 2030. On the left side, you see the result of the technological innovation analysis did by RAILENIUM, and the challenge of this project was how to tackle these innovation trends with the help of advanced technologies by small, medium-sized enterprises. On this cloud, you can see some keywords, what we mean with advanced technologies. There are 16 in the list, and now I will hand over to my colleague Florence from RAILENIUM, who will tell you what special 2 innovation trends are tackled with this tutorial.
Yeah, thank you very much, Lutz. So I will just today present the agenda and introduce the technology innovation analysis as was already introduced by Lutz. And this work was done by RAILENIUM for STARS. So I'm Florence Masbernat, and I'm from RAILENIUM as Partnership and Europe Director. So next, please, Lutz. So here is the agenda today. So after my short introduction, you will have a presentation again from RAILENIUM about this autonomous train program and its major achievements and demonstration by Ankur Matani, who is the Artificial Intelligence Manager. Then we will have a presentation from Alstom by Bastien Simoni, who is Design Authority, about the new ATO generation challenges and European perspectives. And then the presentation by Joaquin Rodriguez, who is research director from Gustav Eiffel University. And then we will speak about the traffic management optimization and the last innovation and state of the art about this topic. So at the end of this session, we will have a question session. So please don't hesitate to put your question in the chat. And then we will take all the questions at the end and ask for you to the speakers, or you can do it, of course, by yourself. Then I come to the purpose of this technology innovation analysis. It was to provide the SMEs an overall picture of the railway major innovation trends and associated advanced technology paths. So this should help them, SMEs, to enhance their capabilities to adopt advanced technology and be more aware about the railway industry changes and innovation roadmap, as well as to highlight some key aspects like skills and other. So this tutorial part 3 objective is to more precisely present but also illustrate with testimonies of major railway sector actors to provide a relevant information basis for SMEs. So next, please. So here it's just a summary of the methodologies that have been used for this technology innovation analysis. So first, you can see this was done in 4 steps. So first, we started from the state of the art from the whole R&D industry and experts of the railway domain, specifically thinking about the ERAC roadmap, but also the SRIA, so the Rail Strategic Research and Innovation Agenda, and the Europe's Rail Joint Undertaking Program. And from this, we extract then the innovation trends and the technology challenges that we have been listing for each changes. So at the end, we obtained 8 innovation trends and 37 technology changes described in hardware and software parts. So the last step of this methodology was to try to propose some key indicators, so to understand better what is the gap to fill to reach these points, and we try to select 3 key indicators. So one is about the time to market, so at which time should be the technology mature for the market, and then the key skills that the SMEs should bring or develop to support this innovation, and the financial effort that is necessary. And we try to say, should it be low, medium, or high, and have some notation. So you can see that all this has been included in a matrix where you can see here the main structure. So first, we describe the innovation trends, the railway segments that should be interested, and then what does it mean for the SMEs in these segments, and then some list of this technology and detail about what does it mean, and the key indicators, and sometimes also showing the top 2 enablers necessary for the SMEs to adopt the technology. So next, please. So here are the 8 innovation trends we have. And today, as explained Lutz at the beginning, the tutorial 3 will be about the innovation trend 2 and 3, about the automated and autonomous train or remotely piloted operation and network management, planning and control. Next, please. So just I will just here highlight some of the points related to each of the topic, and then the actors will illustrate far better than me this. So on the first topic about automation and autonomous train, we need to, of course, design really automated digital systems up to the full automation rate called GOA4 to be able to monitor the open environment obstacle, just like crossover, pedestrian, or animals, for instance. And also, this means to rely on artificial intelligence algorithm developments to be able to better, for instance, use to scan the environment from computer vision and be able to make decisions. So you can see that we have, for instance, the first is to develop new ATO solutions and advanced technology to detect environments and make decisions. So this means to have environment supervising systems based on AI, but also obstacle detection, accurate positioning systems, and of course there is an important matter relative to safety. That we should have a new methodology also to demonstrate safety. So this means to explore new embedded sensors to be able to scan the environment, like LiDAR or radar, because we will have to detect signaling and hazards automatically, and also to develop a new algorithm based on machine learning, data fusion models, to be able to have accurate detection of people or any phenomena in this environment. And then we will need also to develop ATO modeling platforms to be able to test the different kinds of ATO in several configurations, including the degraded modes, and also including, for instance, cartography models. We should also perhaps improve the drones to be used in parallel to produce some information to be transmitted to the train, and as well as the digital automatic coupling technology that will be particularly helpful for freight, but not only, and to develop new sensors and camera. And then, as I mentioned, it will be important to have new protocols for safe and secure, including cybersecurity protocols, and this will be really at the heart of the future standardized technology. And then we can say also that at time there will be nobody on board, it should be able to detect the hazards or the violence by meaning that we will need to progress in CCTV or other sensors, and also respect, of course, the personal data issues from GDPR. Then it means also to implement remote driving and command for monitoring dedicated operations, so meaning for depots, line with low traffics, or shunting. And this will mean also to adapt the communication systems, again, with safe and secure cybersecurity protocol. So, for instance, it can mean to have ultra-low latency video camera, because we will need to have a control in real time, but also to design HMI, so with real ergonomics suitable for drivers, and that should be very close to the environment reality. And then we will have also to develop new approaches, because the traditional one will not be relevant, to prove verification and validation of the solutions. Next, please. Okay, so regarding the innovation trends of network management, planning and control, of course, this is a very important topic, also like the previous one, because we need to drastically increase the capacity of the railway system. So this also will contribute to this in order to ensure the competitiveness of the railway. And we will need also to develop new services that will be based on digital technology mainly, and thanks to this, and to have really work on network capacity modeling, timetable planning, and also the demand forecasting, both for passenger and freight, as well as the rolling stock capacity assessment. So, for instance, we'll have to improve the train planning and to have a real-time forecast of the transport demand. So, and as well as being able to have a responsing transport network planning and routing and capacity management. So this will mean that we should have a better prediction of loads, both for freight and passengers, and to be able to provide more traveling comfort, but also to synchronize better the train traffic with passenger flows. So this will mean to have more integrated handles the services and devices to be able to evaluate the capabilities, the best route, the arrival, for instance, but also to be able to build and deploy some planning platform that will be based on harmonized methods to plan the capacity, but also on algorithm that will support the decision making, for instance, to find the best route. And this also means that we will be relying on centralized databases built on data conceptual models to be fed by all the actors. And this also means, for instance, to incorporate sensors networks on wagons for producing this data. So then also we will have to deal with the last mile connection, for instance, for shunting, yards, terminal, and be able to have relevant HMI interfaces and handheld, again, devices to orchestrate this yard management and the logistics associated. And then we will need also to digitalize and partially automated manual processes that, for instance, should be replaced by dedicated HMI interfaces and devices to support this. And this could help a lot to impact on the maintenance and the spare part services, being more and more converted into digital operation and services. And also, of course, this means to connect with the train on embedded sensor networks. At the end, another important topic will be to organize the cooperation planning between all the multi-actors, especially at cross borders. And this will also involve digital tools like interoperable software platforms, and also based on management tools for planning, decision making, but also sharing data and conceptual data model. And so also at the end, and it will be also necessary to develop new software platforms to verify and certify the load transported. So it was just to give you a general picture of these trends and the contents in terms of advanced technology. So you can see that mobilize, of course, a lot of things like AR algorithm, like sensors, like IoT, of course, and communication systems, safety, and so on. And now I think the best is to let the floor to my colleague Ankur that will illustrate with clearly concrete achievements what means an autonomous train. So please, Ankur, let you the floor. We cannot hear you. If you, perhaps your microphone is...
Yes. Hi, everyone.
Thank you.
Thank you, Florence. So I will be sharing my screen, probably.
Yes, good.
Yep.
We need to... Yeah, very good.
Yes, okay, perfect. So hi, everyone. My name is Ankur Matani. I'm a research engineer at RAILENIUM, working on artificial intelligence and computer vision issues, mostly for autonomous trains projects at RAILENIUM. So the background of autonomous trains research projects is the constant evolution of technology in the field of transport and the need to develop safer, faster, and more efficient solutions. Research advances in AI and connectivity make autonomous trains possible and technologically possible. So I will be generally presenting what we did in terms of autonomous projects in France, actually, and then we'll deep dive into the main concept of the autonomous trains, what are the subsystems involved, and what are the technical and scientific challenges that we faced, which will be mostly based on perception systems, so based on sensors. So first of all, the autonomous train is a disruptive innovation. We started having some first discussions in 2016 in RAILENIUM, but also with SNCF, the French operator. And then in 2018, we launched two huge projects of a budget of 60 million euros that aim to develop and build up two autonomous train prototypes. The first one is a passenger service train, and the second one is a freight autonomous train. Both of them have similar and also quite different use cases and subsystems to develop. Most of the general subsystems are based on driving, telecommunication, geolocalization of the train, and then all the perception systems that can help the train to drive. So they process data based on sensors and then provide enough information for the train to guide his driving actually. So we can find out in these perception subsystems many use cases that aim to detect objects, anomalies, or any useful information. We have been working on several subsystems, monitoring of the environment, for example, signaling detection, cartography or obstacle detection on board, or passenger relations also. All of that, all of these subsystems were developed in these two projects during the project phases in between 2018 and 2023. So we went into real site testing, and that's the next slides I'm going to present. So first of all, what's a perception system? The basic concept is to work on sensors, so onboard sensors that capture data. We can find out many existing sensors on autonomous cars, for example, LiDAR, radar, different type of cameras, video surveillance sensors, positioning sensors, telecoms, and many more that collect data, process them on embedded systems, servers, and then output some very useful information that will be used to a decision-making module. The idea behind the decision-making module is to rely on hypothesis and the most available information to avoid collisions, speed limits, and work on the tractive effort and braking control of trains. And then all this information is directly given into the autonomous driving system and applied to the guidance of the train. So I believe for a more contextual view of the autonomous train architecture, the next presentation will be very precise about it. Now, let's talk about some use cases. So we've been working on them, implementing them on these two prototypes, and testing them on site. So some of these use cases were about detection systems. The idea is to work on mostly images that give us enough information to detect some elements, so extract features to then detect some very useful elements such as traffic light recognition, obstacles detection, pedestrians working in the railway domain, localizing them, and estimating their distance, for example. With all this information, the train can brake or have the correct action to make to stay safe on his track. Just a quick video on how we worked on segmenting the railway tracks. So that's the circulation area, and then the detection objects of pedestrians, other vehicles that may be future obstacles or future anomalies for the train. So these systems were all implemented on embedded servers on the trains, and then were tested live. Some other use cases could be infrastructure monitoring. So the autonomous train has to work on his infrastructure and independently of it, recognize all items that can with time degrade. So we can find many degradations and defaults on the tracks mostly, but also on level crossings, on engineering infrastructures like tunnels, bridges, depending on the area of exploitation of these trains. Other use cases could be also fire detection or luminous signal detections. So that's what we can see in the video below. So all these scenarios were worked on like in real-time systems and optimized to work on very minimized embedded systems and servers also. Talking about graphic cards. Other use cases, so that's a video of what we can do with a microphone. So you probably have the sound. We are going to pass on some bangers, firecrackers, that's used as a audible alarm signal for the trains. And this demonstration is to show that we're not only working on images, but also with signal processing techniques and state-of-the-art methods to process this kind of data also and have some useful use cases. So that could be, for example, to provide the information that today the driver has with his ears, for example. Other use cases based on audio signals could be the noise of wheel flats, signals of underbody impacts, or other malfunctions of the inside of the trains, such as whistles or audio speakers, for example. Next step is to go further with the decision-making module. So here we're presenting a decision-making and based on the simulations. So it takes decision based on the detections that we can see of these pedestrians, and it applies brakes on these tramway simulations. So what we propose here, it's collision avoidance methods for longitudinal driving. So it's based on also neural network architecture, so AI, incorporating auxiliary predictive tasks also. So predictive tasks of future movements of the train and of the obstacles. And finally, it was tested with on board on the freight trains and also in the simulations. So these simulations helped us finding the best optimal parameters to get the best speed curves that was then implemented on the freight train. And some other, so there are two next slides on two different use cases related to passengers. So that's specific to passenger commercial trains. What we can find here, it's recognition of scene of violence. So that's something quite common that can occur, and when there are nobody on board, we have to take action also. So that's based on this video surveillance camera, we can also provide this kind of violence detections or even faint detection or disease, for example. So that kind of information can also have a huge impact on driving. So detecting it as fast as we can, and giving up the information to the driver or the autonomous system or even the supervisor is also a challenge in this kind of projects. Some other challenges like subsidiary that will give more information to the driving system could be also having damage to the train, window tagging, or other warning signal, for example. Or one of the issues also with unattended luggages is that they can they can have huge impacts on the driving also and all the flow of traffic of railway traffic. So detecting them and signaling this information is also a challenge and a huge issue. And finally, the last one is the passenger access. So here it's working with the doors. The idea is to monitor the opening and closing doors and the obstacles in between. So it's to the autonomous driving system has also to control the doors and optimally close and open the doors at each station. That will have impact on the traffic flow of trains, of course. So the idea is to use a distorted camera to detect from the sailing all the pedestrians and all kind of obstacles, so bicycles, bags, huge bags and all, blocked into the between the doors for a long time. When it detects that, in the test we made, there was an audio message that was sent, and if the pedestrian or the person is still blocked, then there's someone from the station that comes and help deblock the situation. Finally, just a quick overview of more challenges, because that's only based on perception systems. There are many more other challenges also, such as legislation and regulations. So a suitable regulatory framework is essential for the safe and efficient deployment of autonomous trains, of course. Then the integration of existing systems. We cannot work on completely new autonomous trains. We have to work on the existing trains and infrastructure and upgrade it at low cost also. So that's also the cost issue is also something. And then data security. So Florence talked about it just before. So GDPR, of course, but also cyber attacks, data governance, use of responsible AI, for example, for ethical issues, and also for video protection. That means juridical and inquiries, for example. So that's just a quick overview. Don't hesitate to contact me after this workshop, and we can talk more and deep dive into details of these challenges that we developed and that we are pursuing with SNCF and other partners in France and Europe. Just in terms of conclusions, so autonomous train research projects offers enormous potential for the future of rail transport. And despite the challenges, the preliminary results that we obtained in these projects, but many more are available in other projects, in European projects, Toro, for example, in automated train with Dutchban or other projects, offers something optimal for the future of the railway traffic and traffic management also. Despite the challenges, the results are encouraging and pave the way for continued improvements for efficiency, safety, and sustainability of the rail system. So thank you for your attention, and if you have any questions, I remain available. Thank you.
Yeah. Thank you very much, Anko, for this presentation and showing both results, but also the future challenges, because I think we are not today completely ready to deploy the autonomous train, but it was a good, as you say, a good way and a good pavement for this. I don't know if there any question? Yeah, Lutz, what you said.
Yes,
so maybe Anko. Yeah.
This question was already raised before the presentation of Ankur starts. Maybe it refers also to your presentation, Florence. But as you are from the same organization, maybe you are free to answer this question, you, Florence, or you, Ankur.
Okay. I don't know, Ankur, if you have, but yes, FRMCS, the future railway mobile communication systems. Of course, this is really an important, I would say, topic for railways at the moment, because we are completely changing of forgetting the previous communication systems and now going through the new one, compatible, I think, with 5G and 4G, and this challenge is also, of course, very important for digital applications, and certainly, if the question is that will contribute to this autonomous functions. And today, I can say that we have some R&D programs dedicated to this application that are with, like SNCF, and of course, we're very concerned by this, but also for instance, the German is the same. They need to work on this transition. And about the drones, maybe, Ankur, you have some idea about this?
Not really.
We were interested in this during the program, but I think I think it's very interesting to and also there are new, I think, programs with drones to develop drones application for railways. So we perhaps dedicated to some particular application, but this could help because we will need to have on board real-time data and don't know if there is a link between drones and FRMCS, but of course, everything should be compatible.
Yeah, maybe it could be further discussed on a bilateral basis. The owner of the question also wrote his contact data into the chat. Is Peter Milander from Sweden, and maybe he has also some fruitful input for your further work, and you can discuss it for sure bilaterally in a good way. Now, there are no other questions for the moment in the chat, but if you have an urgent question by now, please raise your hand and open your micro and then raise your question. Seems not to be the case for the moment.
Yes.
I'm still collecting, and be sure. And so I would say, Florence, it's your turn to announce the second speaker, and I will change your slide.
I think I hope the second speaker is
is
Bastien
in the line. Yeah. Yes.
From Alstom. So now we let you the floor, Bastien. Thank you very much for starting your presentation.
Good morning. I will share the screen if you agree.
Yeah, you could do so without any issue. Yeah.
So can you see the screen now?
No, I can
Not
see
yet.
only you. Now
it's good.
It works.
Now it should be good.
It's great.
Okay, good morning, everyone. My name is Bastien Simoni. I am design authority within Alstom for what we call the onboard CCS, the control, command and signaling, so mainline signaling on board, with a particular focus on ATU up to JOA4. Before this position, I was system architect also on mainline CCS on board, and especially on projects like the autonomous freight train project that you have seen in the presentation before. I was the project architect of this. And I was also involved in European project for standardization. And now this is, so to say, my full-time job. And we are going to discuss about autonomous train operations. So first question is, of course, why are we doing this? The purpose of ATO. In fact, we have several answers to that question. And one of the answers is the famous capacity increase that we expect from the existing infrastructure. So basically, it is about bringing more signaling and less concrete, as some customers would say, to have more trains on the existing infrastructure to support the modal shift from the roads and the planes to the rail. And by doing this, of course, we make the system more attractive. But how do we do this? With automated driving, we harmonize the driving of all trains or fleet of trains on a given route of the infrastructure. And this is how basically we increase the capacity thanks to ATO. Not only, of course, ATO was one part of the system, but it helps already a lot. Then comes the question of the flexibility for the railway undertaker, so the user of the system, to use its trains how it wants, to be more flexible, and also to optimize the operations when we deal with, for example, movements of trains that are just costs. So movements of trains between stations and depot, or garage yards, or shunting, this kind of things, where there are no passengers, so there is no money for this. This is only a cost. And this is, of course, needing today resources, human resources that are more and more scarce. And so human resources could be reaffected to operations that really bring the value and not technical movements in depot or shunting. Then comes the question of cost. So I already spoke about that. It's about using more the infrastructure. So when you use more an asset, of course, you lower the cost. This is also valid for the trains. The more the trains are used, the more you use the value of the train and your investments. Quality of service. So here we are more speaking about driving styles, for example. So using automated driving is also a way to harmonize the way the trains are driven. And so by harmonizing this, you have a more smooth journey. So for passengers, it's interesting. And by having more capacity, you have more offer of frequency of trains. This is also something interesting for the passengers, for passenger experience, and punctuality and journey times achieved for sure with ATO, but also with a complete highway system that is consistent with it. And this is something very important today, energy efficiency and lowering the energy consumption. When you use automated driving, you have an algorithm that pilots the train that
Sorry, Bastien, I don't know. It seems we cannot hear you.
Me either.
Perhaps you had an interruption.
Maybe you switch off your camera.
Yeah, I'm very
get.
Yeah, I'm very sorry for that. Wi-Fi at my office is very used right now, so
Yeah.
I may suffer from some glitches. I'm
Yeah.
sorry for that.
Okay.
So I don't know where it cut.
You were just speaking about I think the energy importance to
Okay,
have
so
this reduction.
So regarding the energy consumption, this is a topic that is very important today. To optimize the energy efficiency. Using automated driving for trains is something that can help. It depends, of course, of the use cases. If we are speaking about passenger trains, about freight trains, about regional, suburban, and so on. So here you see 40%. This is a best case scenario that you can mostly see on suburban with a lot of traction and stopping. For freight, this is also very interesting, especially in the context now of rising energy costs. So this is something that also interests a lot the users to use ATO technology to reduce basically the energy consumption. So here we spoke about the why, and then if we focus on the how, so here we speak about ATO, so automated up to autonomous train operations. That is incremental, of course, to automate more and more functions for the operations. And basically, when we speak about automation, this has started a long time ago already with what we call the grade of automation 1, GOA 1, which is manual driving, but protected by an automatic train protection system that makes sure that the train stops if the driver passes a red signal, for example. So this is something that exists for many years already. This is already some kind of automating function. This is GOA 1, and you see in the table that the driver is responsible for all the tasks in this table, the ATP being responsible for the protection of the train and its passenger, of course. GOA 2 is a new step in automation for the main line that is quite recent now. You have, of course, ATP that is still there to protect the train. However, a new system that is ATO takes the responsibility for some functions, like, for example, setting train in motion and the driving and stopping of the train. So this is already GOA 2. However, the driver remains responsible for some functions, like the door closure, passenger exchange in stations, and to take the responsibility if we are facing a disruption in the operations. And GOA 2 is something that we see more and more now in the main lines, thanks to standards that have been published some weeks ago. GOA 3, what we call driverless train operation, DTO, driverless because there is no more driver in the cabin. However, you still have a train attendant that may be responsible for the door closure or not, depends on the use case. and that is still responsible in case of a disruption. So this is the GOA3 and the GOA4, which is called UTO, unattended train operation. There is no more staff on board the train. This you see on some metro lines in the world already today, in the urban world. However, in the main line, this is still a dream for a lot of users. This is not a reality today because of the challenges we already mentioned before at the presentation, and I will also mention here. So here we are speaking about GOA, so the what is ATO, and then the way, because of course ATO is something that is of great interest for the European Commission because of interoperability. And so this is something that we need to understand in the context of standardization and the European strategy. Of course, at the beginning of the railways, GOA 0, this was drive on site. So here, this was not a topic to have interoperability. We have driver changes at the borders and so on. The problem began more and more crucial with ATP systems, protection systems that were national systems, and that led to harmonization already 30 years ago with GOA 1 and the famous ERTMS ETCS system, European Train Control System, that is today mandatory on new lines and new rolling stock that is quitting a factory. So this is for GOA 1. For GOA 2, for ATO, the work has been done in Shift to Rail, started by Unisig and the users, and then led in Shift to Rail some years ago. And that led to the standardization of new functions, bringing ATO GOA 2 as a standard that you see now in the technical specification for interoperability, CCS, Control Common and Signaling, that was released on the ERA website some days ago. So if you go on the ERA website, you will find the new TSI, STI TSS. I have problems to say that, TSI CCS, and that you can see the subsets that are mentioning ATO and that you can read if you want to. And GOA4, this is of course the goal. GOA4 brings new challenges. The work has started in Shift to Rail in 2018 to switch from GOA2 to GOA4, and the work will continue in a program that I'm sure all of you already know, which is Europe's Rail Joint Undertaking with different groups to break the standardization of the functions, and of course to make large-scale demonstrators to prove or not the feasibility and the working assumptions that we have in the standardization. So this is the way, basically, to the standards. It will take minimum 10 years to achieve something for GOA4. This you have to keep that in mind. It will take time, and in the meanwhile, we need to investigate, we need to test, we need to learn in a try and error mode, obviously, to see how we can achieve GOA4. For what use case, what benefit, and with what technology, because technology is for sure very interesting, but the main aspect here is use case and problems to solve. So this is the way. When speaking about GOA2, so this is already a reality, as I said. I will be very fast on that to explain. So GOA2, we have a device that is ATO on board, help with trackside systems that performs automatically the traction and braking of the train according to some inputs. So the signaling, of course, if you do not respect the signaling, then the ATP, the protection system, will stop the train. The timetable that comes from the trackside, so the operational scheme to follow. The properties of the track, that helps the ATO onboard the algorithm to drive the train in the most efficient way, so to save the energy. The train properties, are we dealing with the passenger train, the freight train, what is its mass, its length, and so on. And the driving logic, that is the algorithm that is made by the suppliers, that is of course the knowledge of the suppliers, to optimize all of this and to have the most smooth ride possible by saving the energy and respecting all the inputs I have mentioned above. So this is already available in the TSI CCS that is 2022 but released this year, and that I invite you, of course, to read if you have the time and the wish to do, so that you can better understand what we are talking about. A small video of tests that were conducted in Switzerland on freight trains. This was the ARC project. So here, basically, you see that the train or the loco is running by itself on the line. The driver doesn't touch anything, and you will see that the locomotive will stop automatically at the station Saint-Léonard. And so here we are speaking about GOA2 because the driver is still there, and the driver has the responsibility to monitor the track, is there an obstacle or not, and to monitor also the exchanges of passengers if we are dealing with passenger trains in the stations. So here you will see the train will stop in a few moments. And you see here on the tablet some indications. This is the interaction with the driver, and now you see that the ATO has stopped, and you will see the remaining stopping time. You see the 15 seconds here. That is the time for the stopping in this test. Now, if we go on to GOA 3 and 4, of course, we have a lot of new functions. Perception. We spoke about it in the previous presentation. Perception is a huge topic for GOA 3 and 4 because you need to perceive what is happening outside the train, but you also need to monitor what is happening inside the train when we are speaking about passenger trains. And this leads to automatic decisions that must be made on board. Because of the time to make the decision. I cannot go to the trackside and then the trackside makes a decision. This is not possible. So you need to have very fast decisions on board. How to achieve this, I don't know today, because this is supposed to be, of course, deterministic, to have some kind of homologation. However, you might have also some kind of AI support or this kind of stuff. This is a huge topic, automatic decisions, and for sure we will have a lot of discussions at the European level to see how we can proceed. You also have TCMS, so the train control and monitoring system, the onboard IT of the train itself. The train is supposed to be intelligent, so the train will have to perform automatic decisions also. If there is a train malfunction, if there is an engine that is not available anymore, and so on, this is the train's responsibility to decide what is the best option for the train itself. So we expect to have TCMS and rolling stock that is more intelligent. That's a very important topic. And of course, other devices that are not part of the ATO world, but that are necessary for the use cases, like the remote driving in case of degraded situations. So maybe we have a pool of drivers that are trackside with some kind of remote control desk, and that can take over the control if there is a malfunction of ATO, for example, or a disruption on the operational scheme. This is something that we discuss a lot with the users. And collection of data from the trackside, because the trackside, of course, has a lot of information that comes from different trains, autonomous trains, and the trackside can make also decisions on the timetable, on the operational scheme, and on decisions to make based on a lot of different information that come from different trains. So you also have an impact on the trackside assets for making a robust operation and to take the proper decisions in function of what has come from the different trains. And this is discussed in Shift2Rail, so in the current X2Rail 4 project, and in Europe's Rail joint undertaking in different groups. So here you see in the scheme an architecture, a system architecture that is the main architecture for ATO up to GOA4, with components in yellow that are the 4 main components for the ATO up to GOA4 on board, but also a lot of different components that address the complete railway system, because when we speak about ATO up to GOA4, we impact the complete railway system. This is not about saying, oh, I have an autonomous train, that's very easy, and that's it. No. This is a misunderstanding. ATO up to GOA4 has an impact on the overall railway system, on the IT assets, on the signaling system, and mainly also on the operations. So we need to have a complete system overview, and only a system thinking about this can achieve a proper implementation of ATO up to GOA4. And so here I would like to stress this message that when we speak about ATO and autonomous trains, we need to have a complete system thinking and a system analysis. Otherwise, it will just be a failure or something that we will implement and that will just not work, because we need to discuss with the highway undertakings, we need to discuss with the IMs, the infrastructure managers, and we need to make it consistent with the overall system, because if you have a super ATO GOA4 on your train, but you cannot have a system trackside that handles the timetable correctly, then you will just have made an investment that will bring nothing. So this is a super important topic, to have a system thinking, and this is what is happening right now in Europe's rail joint undertaking. Last but not least, ATO. We spoke about ATO over ETCS. So automated driving that works obviously only on the European signaling system ETCS. The little problem is that, I'm sure that ETCS takes time to be rolled out, especially trackside. And then you cannot have automated driving on lines that are not yet equipped with ETCS. So this is a huge problem. And so here we speak about migration, how to migrate from the current different highway system in the different countries, still equipped with national signaling systems. And how do you introduce automated driving, even GOA2, so traction and driving with a driver, on lines that are not yet equipped with ETCS. And so here we are facing an important question that needs to be answered. We cannot just sit here and say, no, it will be deployed ETCS and that's it. This is not acceptable as an answer. We need to define migration solutions. This is discussed at European level on how to propose migration solutions. And we at Alstom, we have worked on a migration solution that is based on the perception of the line side signals, which is basically the same as ETCS level 1, because ETCS level 1, you just pick the signal information with some sensors and you put this in the balise, basically. Here we do the same with a camera, so you see this in the video here. And this is a possible migration solution. It's not the only one, but it is a possible migration solution to make ATO attractive. And when you make ATO attractive, you make ETCS attractive. This is something that is very important. ETCS is an ATO enabler, but ATO is also an ETCS enabler when speaking about ETCS trackside fitment. Very important message here. Key takeaways. So when we spoke about the what about ATO, we speak about grade of automation, because we can speak about automatic train operation. We can speak about autonomous train operations, depending on the grade of automation. Mainline ATO is something that is very different than urban ATO, because one can ask, oh, sorry, but why are you making ATO for mainline only now? It exists in urban for more than 40 years, even GOA4. Of course, we do not have the same environment. It's open. We can have obstacles. We can have objects. It is an environment that is very variable, with different regions, different rolling stock, different trackside systems, with legacy systems, with national systems, and so on. And the key topic today is we need to be interoperable and to cross borders without any problem. This is the way. And so this is the main difference with urban, where you still have today systems that are self-supporting, and that's very fine for the use cases. But for mainline, this is totally different. GOA2, this is a quick win. It's clearly a quick win to make the ERTMS ETCS more attractive. However, as I mentioned, the fitment is taking time. It's costly. Will we have ETCS on all lines? I don't know. Will we have ETCS on shunting yards and regional or low density lines? I don't know. So here we are facing some questions that we need to investigate. We need migration solutions, because we cannot wait 10, 15, 20 years for ETCS to be rolled out everywhere to use ATO, especially in the context of energy saving. This is not acceptable as an answer. So we need to define migration solution from now on up to the vision of 2050. That is the vision of the single European highway area with ETCS everywhere. But from now on, we need to define the migration solution. This is super important. GOA4, it opens difficult questions on the operations and the technologies. It is very complex. We need to define the specifications at European level, because we need interoperable solutions. And the large-scale demonstrators that we will see in the next coming years will, of course, demonstrate, validate, or invalidate the feasibility in the next years. And I thank you for your attention.
Yeah. Thank you very much, Bastien, for this very interesting presentation showing, I think that we need to develop, of course, advanced technology and to demonstrate it and to test it, but there is also critical questions about the deployment and how fast we can deploy the solutions, and the question of this roadmap and interoperability. That is a real hard question for many years in the railways. That's progressing, but when you speak about 250, it seems to be not for tomorrow yet. And yeah, we can say maybe we could, I don't know if possible, accelerate this migration and these changes in the railways. We're speaking also about FRMCS and so on, and so perhaps we need to harmonize this and to push it at the European level, as I think it is key for the competitiveness of the railways compared to other modes, in fact. So perhaps it's more a comment than a question, but don't know if there are any other questions.
No questions from the chat, but you have the chance to raise your hand and open your micro.
Yes, and I think well, seems not. Okay.
No.
So again, Bastien, thank you very much. Anyway, the presentation I think is very interesting, and we will distribute it on the Star channel, and perhaps think maybe it could be some exchange with Bastien if necessary on those topics. And anyway, thank you very much for this.
And thank you.
And I will now ask to Joaquin if he can start his presentation. Thank you very much, Joaquin.
You hear me?
Yes, it seems okay.
Do you see my presentation?
And we see it.
Okay, so I can start. Thank you very much for inviting me to give you this talk. So I am Joaquim Rodriguez. I am researcher at University Gustave Eiffel, and I work on traffic management optimization. So in this tutorial, I will present you some research results on this topic of looking at decision problems that were populated all the process of building railway services. So I have to apologize that some slides are still in French. I hope that it will be not a big issue because the key words are more or less the same as in English. So here you can see the process of building railway services. It's a very simple diagram. We can see that at the beginning on the left, we start with the demand analysis in order to define the resources built, meaning, for example, how we have to build new station, if we must to add new lines and so on. So this decision must be taken many years before, 10 years, for example, or more. Also, we have to take decision if it is railway undertaking to buy new rolling stock or to hire new crew. So after that, we have also a strategic decision regarding the definition of the line. This is line planning, meaning, for example, to define what will be the stop patterns, what will be the frequency of the services, and so on. And we move to the tactical phase more or less 1 year before. It's the time to define timetables, meaning that at what time the trains start, at what time they will arrive at different stations. And next, we have to assign the different resources to make these services. So we need, for example, of course, rolling stock. So we have to assign rolling stock, and we have to assign crew, which is the next step and the last step before we apply this plan, we start to define at real time what we have to do to decide when we are faced to some situation where the plan doesn't work due to many events, unplanned events. And we will see more in details the last part of this process. But we will see other decision problem in tactical and in strategic phases also. So before to look at these different decision problems, I would like just to mention the main barrier, scientific barrier of these problems. The first barrier is that we have many times, problems that are very huge regarding to the decision and the context we are working on. We have also to face multiple actors, multiple criteria. So this increases the difficulty of this decision problem. Another part that is difficult to manage is what we name variability of the stochasticity of the problem. For example, normally when you plan a stop at a station, a dwell time, this dwell time is not always fulfilled. We have some time to increase due to passenger behavior or to a decision of the driver to increase the dwell time. Also, the running time between stations are different depending on the driver. Of course, if we apply an autonomous train, this will reduce this variability and will define new kind of problem. And the fourth barrier is that we always solve this decision problem sequentially. We don't, many times we don't merge the different problem into one problem in order to have better decisions. And this is due to the difficulty of this problem, which are quite large. And we will see some example in this presentations of this situation to be ready to integrate some problems. So before that, before looking at different problem, I will just focus on what we call the different level of representation of the infrastructure. So traditionally, we use it what we call macroscopic view of the infrastructure, and after that we look at more detail, and this is the microscopic approach. So if we look at microscopic view of an infrastructure, it is a network of the different stations. Like here we have an example of the north of France, and each node is a main station, and each arc represents the line linking this station. And for example, if we look at this line that link the station of Lille to Dunkerque, we have a view of a time distance diagram where we put at each vertical axis points of the different stop station. Here we have on the bottom Lille, Armentières, Hasbrook, and Dunkerque here for this line. Now, if we look at the time axis, we can put the evolution of the different train in this diagram. And we can see that if a train starts in Lille, we can see that the horizontal line means that the train is stopping at this station. And this train stops at all intermediate stations, the blue train. On the contrary, the next train, the green one, will only stop at Armentières station. And the last train, that is direct and express train, will not stop at any station. It will only stop at Dunkerque, and it will overtake the previous train at Hasbrook station. So this is a view, microscopic view of the services, where each train is represented by a train path, and it is viewed as a point. along this time distance view. Now, if we look with more details, we look, for example, at a node, for example, here, the Lille station, and we continue to look at still more details. We look here at the part of this station where we can see the details of the signal positions on the track. We can see also the details of the track section limits where we can detect the position of the train by the signaling system. So we can have here in this view very details of the infrastructure, and we can put that in the time distance diagram also. And in that case, the train are viewed not with a point, but also with 2 points, the head and the tail position. And if we look, for example, at this track circuit, we can see that the train is detected at that moment, and he will clear this track section at that moment. So we can fill a rectangle of use of this in part of the infrastructure. So the view of usage of the infrastructure is a geometrical rectangle. But this is only the detection. If we now look at what's happened, if we take into account the signals and the number of aspects, for example, we know that we have to enlarge the rectangle of using this part of the infrastructure, because when the train will run at with free where in this line, that means here you will have a green aspect, open line aspect. We need to enlarge the rectangle of use in order to take into account all the details linked to the signaling system. Now, if we apply this reasoning to all the track circuit, we obtain this pattern of using the infrastructure. So this, what you can see here is the pattern of a microscopic use of the infrastructure, which is named a receive model, and which is used also in other by other laboratories or that develop this approach of microscopic view of the infrastructure. So we have developed a formulation, a mathematical formulation of these patterns, which name is receive, with different techniques, either with constraints programming or with optimization mathematical programming. So I will just speak about receive MILP, which is mathematical optimization now. With this approach, we can have move to an important step that now we can use microscopic approach to manage and to optimize the railway traffic. So now here is just an experimental scheme of using these models. Of course, we not apply this model directly to the infrastructure, due to the cost, of course. So we apply and we test our model in its simulation. Simulation replace the real railway system. And we apply the models and the solution algorithm. So here is just a sketch of the experimental platform we have in Gustave Eiffel University, where we manage different case studies we have used during the different projects. We have used this approach and the different model we have developed, and tools that use to test and to validate our approach. We have used also different simulators. I will not go too much in details on this aspect. Now I move to the different problems we can solve and we have faced during the building of the railway services. We start with operational decision problems. And for example, the first problem is how we can reduce the number of routes with equivalent quality of solution. So to do that, we have used the receive model, and we have used also ant colony optimization to reduce the search space. So here we have the example of the case studies we have worked on. It is a Lille-Flandre station, and it is a part of a railway line between Le Havre and Paris, and Hazard. So you can see that there is too much number of routes per train. So we reduce the number of routes by using ant colony, and the ant allow to reduce the number of routes in that case. These are the main result of 2 PhDs we have developed with university raw material. We have worked also on what we call a decomposition approach or cut-in-place methods. The approach is to have a decomposition of the difficult problem into two problems, a master problem and slave problem. And we try to find in the slave problem what we call cuts, that mean constraints to reduce the search space. So this has been done also in the framework of a PhD in IFTA, which is a former name of Université Gustave Eiffel. And we have worked also with an Italian university, University Ca' Foscari of Venice, with Professor Raffaele Pesenti, to define this kind of cuts, which is a relation between routing decision and scheduling decision order between trains. And with this cutting plane method, we have reduced the number of variables, and we have a significant performance improvement of the receive mill model. Another problem is to apply this microscopic approach to a larger scale, and for example, to a network. So the approach was first started during the Shift to Rail project, X to Rail, and with the RAILENIUM subtracting state. So we define a coordination master problem that manage different sub-problem in each station, for example. And each station, we solve the dispatching problem, and we provide Bender sketch, that means valid inequalities that are added to the master problem in order to go to a valid solution that allow to coordinate the different stations. So this will continue, this problem will still continue in the next shift, the next journey undertaking, Europe's Rail, now in the Motional project. Here is another formulation that use what we call option intervals in constraints programming formulation, and that will allow also to add a new decision, for example, to remove stop, to add new stop, or to cancel some trains. And this is a difficult, much more difficult problem than just scheduling and routing problem. And this can be performed with this new formulation. We have seen that we have different also problems that can be merged. In that case, we can also take into account what will be the best speed profile that must be applied during perturbation. So if you have to decide schedule and routing, we also integrate the choice of the speed profile in the model. So this have been done first in a PhD thesis with University of Salenzo, and we have continued this approach to solve with ant colony algorithms with the University of Bologna to define the best choice of speed profile. Now here we have another kind of problem in operational decision is how we can share the capacity between maintenance work and train circulation. So this problem was formulated also in mathematical approach. It was also a PhD work with RAILENIUM. And here we have made experiment with a lot of instances, and it has been validated in a case study of the line between Paris-Le Havre. And here we can see the different work windows to maintain this line that have been tested and that has been provided by the infrastructure manager in order to validate the real solution to allow a good management between maintenance work use of capacity and train circulation. Now I will speak about another case study, another problem, which is to manage what is done in a station and what is done near a station. That means the parking trains, washing train, maintaining trains, so close to the station. This is very important because that means we have to have an integrated management of the rolling stock and also the traffic. So this is a very special case of integrated different decisions of rolling stock management and traffic management. This is a huge problem which have been formulated with more than 80 constraints. And we have seen that it's, of course, very difficult to solve this problem directly. And we defined different scheme of solution of these 4 problems in order to solve partially some problem and then come back to that problem after I've solved the other problem completely. So this, I will not go in details of how we find some good solution to manage rolling stock and also manage traffic close to big station. This is also a work that has been done with a PhD student and SNCF Réseau, which is a French infrastructure manager. Now I give just an example of a problem we have solved at a tactical level. It was a work that have been done with a partner, Italian partner, which is Trenolab. It is a small infrastructure, a small company that provide consulting on traffic management and tools. So the contractor was the Norwegian Railway Directorate, and the goal was to provide a support tool for multi-objective railway timetabling. That means providing in different contexts what would be the optimal timetable regarding to different objectives. So to do that, we provide a tool that use ant colony approach and mathematical formulation of railway timetabling. So this has been provided to the Norwegian Railway Directorate and validated by this contractor. So now I'll also provide another tool that is developed at Tactical Decision. Its name was Optimum. It is a passenger-oriented modeling and optimization of the railway transportation plan in mass transit system, that means in urban context. And the goal is to integrate what we call line planning and timetabling. I just recall that line planning is to define what will be the stop pattern and what will be the frequency of the lines. And timetabling is to define each timetable, each start and arriving of the trains in an infrastructure. So in this case, we have to take into account the passenger view. That means the passenger travel time, the demand elasticity, inline planning, of course, and the passenger comfort. These software have been validated and now is in an industrialization phase for SNCF Transilien, which is the operator of railways in the Paris area. So now I've moved to the last phase of decisions, which is a strategic decision in order to find what is the better view of the capacity. So that in that case, we have to solve what we call a timetable saturation problem. So timetable saturation is that starting with a timetable in a line or in a network, we try to add the more train that we can. So in that case, in the first project, which name was CG Freight, the goal was to have two objectives: to add the more trains, the total number of trains, and to add also freight trains, because the goal was focus on freight problems, insertion in railway network. So we have these two objectives. So we develop a B-objective formulation of the mathematical formulation at a microscopic level. And we can see in the bottom part here at the left that all colored train paths are the additional trains, either passenger train or non-commercial train also, and the number of freight trains also. We can have had 300 trains, and among these 300 trains, we have more than 100 trains freight in addition. But as we add more and more trains, the problem also will be what will be the stability of this timetable. So this was the goal that was studied in this PhD of University La Sapienza, to also have a compromise between the saturation and the stability. That means adding more margins to the trains in order to have more feasible in reality due to the stochasticity of the real situation. So that's end my presentation. I will just give you some perspective of work. You all have heard about new kind of mobility systems on mobility solutions. So we work with SNCF and also in a French project, which name is FlexMove. That this project goal was to use tracks that are no more used by trains with the new system that are mixed between road and railways. And also the perspective of optimization traffic is to use artificial intelligence technique. And in our case, we are working on projects to use both artificial intelligence learning approach with optimization techniques. So we work on project with SNCF, Deutsche Bahn, and also German academic partner has Technical University of Dresden. Another a perspective which is very important regarding to the previous presentation is to extend our model for new signaling system and mobile block signaling. Moving block, sorry, it's not good translation, is moving block approach, and also virtual coupling. This was done in performing rail, and this will continue in a PhD work with the Technical University of Delft. And also the last mention I would give you is about another project with name is Sorted Mobility to go toward autonomous traffic management, meaning that trains would be agents that could negotiate between both different trains in a local approach in order to have a big decision at a central approach, and we will try to look at what will be the benefits of local decisions regarding to centralized decisions. So thank you very much for your attention. This is the last.
Thank you very much. Thank you very much, Joachim, for this very pedagogic presentation and so complex topics that you have illustrated some major challenges and perspectives on it. Maybe I have a question concerning is there a link, maybe you mentioned it, between the ATO developments that we have seen and the traffic optimization tool? Do you have a specific project on it, or is it?
There is no direct link for the moment,
yeah.
But as I said, the ATO new system will provide a new parameter of the problems. For example, we have more deterministic time of running time between stations. We will have also more possibility, for example, to manage rolling stock between the yard and the station. That today is more difficult to model this problem, because you have to find a driver, you have to look at if there is a possibility of routing the different train. When we are, if the train can be drive with an autonomous approach between a yard and a station, it will be more easy and more flexible when we are faced to perturbation. For example, the rolling stock that is planned doesn't work. We have to assign a new rolling stock. We have and we know how long it will take to provide this new rolling stock at the right platform for the passengers. This is an example, I think, that will change this problem formulation and performances.
Okay, so I think when what I understand is if we have an autonomous train, in fact, you will have more precise data, and you will have more flexibility to manage more efficiently the railway network capacity, in fact, and this could help in a way.
Yes. For example, the other example is in urban context. Sometimes it's difficult to reduce the services, to stop at a station and to make a turn back, because, for example, the driver should have to stop at the next end of the line. But if there is no driver, it will be more easy to apply this turn back decision. So this changes the data of the problem, of course.
Yeah.
As we have more flexibility, we have more decision, and we have more but we will have more difficult problem, because the surface space will be more huge, of course, also.
Yeah. So
interesting
for
us,
good news for research anyway.
It's
not finished, we understand this. Perhaps another question, because you speak about intermodal, for instance, the flex move, and we have also some links or some with aeronautics, for instance, methods like what is done in César. Do you have?
We have studied the comparison between aeronautic and railway, because my colleague Paola Pellegrini worked a lot before joining our team, work on airplane traffic management, and she knows very well this problem. But in aeronautic, the operator are also in charge safety. So this change a lot the problem, which is very different in railway. In railway, normally in normal operation, a dispatcher has no safety responsibility. It's based on the technical components more than in a human components, except driver, of course, that must fulfill the signaling system. But if we have driverless, there is almost no human, and in that case, this is a very different aspect of with aeronautic, because the other aspect is that we have in train we have just one dimension. It's a line, and it's very difficult to overtake, and so on. In a plane, we have 3 dimensions to manage. It's more I mean that conflicts are more easy to solve with just changing the height or something like that, because we have not so huge difficulty regarding to the capacity. In trains, the capacity is more scarce resource, much more. That is why we must look at all the detail in order to have more better use of the capacity. It is important to avoid just a rough view of the capacity. We have to look at all the detail, because it's very expensive. Even a small part of the capacity, it's worth to work on.
Yeah, certainly. Okay, thank you very much, Joaquin, because I think we are running on time and we should now close this event. And I would like to thanks a lot all the speakers that have provided great presentations, and perhaps Lutz, the final conclusion.
Yeah, only two words. Thank you also to the presenters for these interesting presentations. And yeah, that is the end of this tutorial. I would not forget to mention that the recordings of the STARS tutorial would be available on the YouTube channel of the STARS project. The link is already in the chat. And Shona is going to write something. Maybe we can get it. And before observing once more the chat, I would like to invite you to the last STARS tutorial of the technological innovation analysis, and I guess it's also the last STARS tutorial during the STARS project. Maybe you can say some words on it, Florence, and I will put the registration link for sure in the chat.
First, thanks also all the participants, because I see nice comments, and thank you for this. And I hope, yes, we will enlarge our audience. And yes, the next, and it will be on the 21st of September. I think it will also very, very interesting one. And we will have a presentation from SNCF about the new generation of light trains that should be for the tracks. Well, what we call it, capillary tracks, not the main lines, but and we have also a presentation from I think Fraunhofer from Berlin about the noise and the simulation of the noise of the train passing. That I think is very interesting, because noise is also, with increasing growth of traffic, a very important topic, and this will be. And I would say also that we will have an intervention of a digital startup called MacLedger that is very, very also interesting to present the new services, that also digital services that we can manage to develop the multimodal and intermodal transport. So everybody is welcome, and of course, I hope we'll have a good audience again. Thank you very much, Lutz, for organization also and supporting this.
Yeah, you are kindly invited for sure to register for this tutorial, as well as you have been registered for this tutorial. And I guess it will proceed in nearly the same manner than today. I have nothing to say for the moment, or only have a nice time, and see you soon.
Have a nice time and lunch, maybe. Ciao, ciao to everybody.
Yeah, bye-bye.
Bye.